Good evening, ladies and gentlemen. Welcome to BrisScience for June 2017, hosted by the University of Queensland. This is our free public lecture series on science, where we bring you not just the best scientists, but also the best communicators. We're tonight here at the State Library of Queensland, a new venue for 1 week only, which is very exciting. I'm your MC for this evening, Joel Gilmore. Before we start, I'd like to acknowledge the traditional owners of the land on which we're meeting tonight and to pay my respect to elders both past and present. Tonight, we are going to be taking a look at the power systems of the future, a very topical issue at the moment. It seems like you can't open a newspaper or actually ABC Online without seeing a story about what should electricity markets and renewable energy and coal look like in the future. So tonight we have the wonderful Dr Jenny Riesz from AEMO to provide some background and directions for that. First, a couple of bits of housekeeping. So Jenny will do a presentation first, after which we'll take questions. You would have received on the way in a question slip, which you can write down your questions on. We'll collect those, and I'll ask as many of those as we can at the end of the talk. Or you can ask your questions over Twitter, #BrisScience. And you can use this opportunity to load up Twitter and check that your phone is on silent right now. Great. Afterwards, of course, we will have food on the lovely terrace outside on the State Library of Queensland, and Jenny will be available for more discussions as always. Okay, so it is my great pleasure tonight to welcome Dr Jenny Riesz, who's a principal at the Australian Energy Market Operator, or AEMO. Before that, she has worked as a consultant, as an academic researcher on 100% renewable energy systems, but I've actually known her since we first studied physics together as undergrads at the University of Queensland. So you will soon see that she's a highly sought-after public speaker with a real passion for energy and the future of Australia, and no pressure, Jenny. Just thought I'd set that up there for you at the start. And so on that note, please join me in welcoming Dr Jenny Riesz.
Okay, thank you, Joel, and thank you everyone for coming tonight. It's a real pleasure to be here. So, as Joel said, I have had a path through time that involved working at the University of Queensland. That's actually me in our clean lab. I did research there looking at melanin skin pigment, because we were interested in it for photovoltaics. I worked for a while in industry and consulting, back in research at the University of New South Wales, doing research mostly on 100% renewable systems, as Joel said. And now I'm at the Australian Energy Market Operator, AEMO. So when we think about renewable energy and we think about systems with lots of renewable energy, people tend to think about photovoltaics and wind turbines. And we think about, how does that system work? Because you don't know that they're going to be there all the time. So how can you possibly create an effective, reliable power system out of just renewable energy? But we somehow forget that there's all these other options available to us. We've also got geothermal, hydropower, biomass, concentrating solar thermal energy, and all of these technologies are available on demand, and they're very similar in a lot of ways to the power system that we run today. So by mixing together all of these technologies, you can create power systems that are very reliable, the same as today, and made from potentially 100% renewable energy. And this is the sort of research that I did when I was at the University of New South Wales. But the question always comes back. But the sun doesn't always shine, the wind doesn't always blow. How can it possibly work with a high renewable system? So I'll give you an illustration of how it might work, one possible way from the research that I did. So this graphic is showing you an illustration of our power system today. It's the amount of capacity that we have installed to meet demand. And at the moment we have a lot of coal, a bit of gas, some hydropower, and a little bit of wind and photovoltaics on the top. And our demand, the electricity demand on our grid, varies from about as low as that to about as high as that. It moves up and down day by day, and we switch on and off plant to match against that day by day. So it's always within the range of what we've got. Now, if we look forward to a system that might be 100% renewable energy, it will probably look something like this, or this is one way it could look. Vastly more capacity installed, most of that being wind and photovoltaics, delivering most of our energy. So something like 70 to 80% of our energy could come from wind and photovoltaics because they're so cheap. They're the cheapest type of renewables that we have. So they produce all our energy, but we still have this firm capacity at the bottom. We can have things like, in this particular example, concentrating solar thermal, biomass, the same hydropower that we use today, and we can switch those plants on and off to match against the demand varying between these levels. So you can see there's actually enough firm capacity here that even if there was no wind and no sun, we could turn on all the other plant and still meet demand. So in those very rare circumstances where that could happen, the lights don't go out. We can still have plant available. But the key difference is that most of our energy is coming from these guys, the wind and the PV. So what we're using here is peaking plant, particularly in this example, biogas turbines, which would run very, very rarely, but are there for when we need them. And that's actually a very cost-effective way to have a reliable power supply. So this represents a huge paradigm shift in how we think about our power systems. We're going from something where we have a lot of base load technologies that run pretty much 24/7, and our peaking and intermediate plant on the top of that varying up and down as our demand varies up and down, into something where it's the variable renewables, the wind and the PV, that ramp up and down and do what they do, giving us their cheap energy. And then the dispatchable renewables sit on top of that and match up to the demand to make sure that we've always got the reliable electricity that we need. So when people say, but the sun doesn't always shine, the wind doesn't always blow, this is pretty much busted. This is really not the challenge that we're worried about these days with high renewable systems. There are a suite of things that are challenging about running a high renewable system, and I'm going to spend the rest of the talk today telling you about what those things are. But this is not the primary concern anymore. We've really moved on from worrying about this. So as we said, I work for AEMO, the Australian Energy Market Operator, and we're the organisation that is basically responsible for keeping the lights on. We don't own any generators or any network or assets, but we're responsible for coordinating the whole system and making sure that everybody is acting in the way they need to act to make the system operate properly. So we run the national electricity market, which runs right from far north Queensland all the way around up to Adelaide and through down into Tasmania as well, supplying about 85% of the electrical load in Australia. Now, when we're looking forward, we have responsibilities for planning this grid forward in time and making sure that it continues to be reliable. And we're seeing a dramatic transformation underway. So we're moving from our present power system, which, as I said, is a bunch of coal, some gas, some hydro, and a bit of wind and PV on top. Looking forward in time to a power system that's really different. A lot less coal, with a lot of it retiring, maybe some more gas, but a lot more wind and PV. We're looking at particularly even a lot of distributed plant coming in. So things like solar panels on people's roofs becoming a major part of the system. And this is a very different power system for us to be operating. So I'm a part of our Future Power System Security Program, which is all about looking forward in time to anticipate what's coming and make sure that we can address it early to manage this transformation. So we're all about adapting our functions and processes to deliver ongoing power system security and reliability. And that's about identifying challenges, prioritising them, quantifying them to see when they're going to become a problem, looking at the solutions available to us, and then implementing those solutions in whatever framework makes most sense. So when we look at the challenges that we are working on in terms of making a high renewable grid a possibility in Australia, the challenges fall into 4 broad categories which are related to the aspects that make renewable energy different, or some types of renewable energy different. So renewables, like wind and photovoltaics, are often variable and uncertain in their availability. They have very low operating cost, so they're expensive to build, but then once you've built it, the energy is essentially free. And that has all sorts of interesting challenges for the way that our market operates and the way that prices are set in that market. Things like wind and PV are non-synchronous, which is about the way that they connect to the grid. And I'm going to tell you a lot more about this and what that means. And renewables like rooftop PV are distributed because they're individual small systems on people's roofs rather than big central power stations that we can control and direct. So thinking about variability and uncertainty, there's all sorts of challenges around things like forecasting, for example. So we use very sophisticated forecasting systems based upon the weather to understand what the demand is going to be. And we've had to add to that systems to look at what the wind is going to be, what the solar energy is going to be, how that translates to the generation from a whole suite of different power plants, and to plan and operate that system 5 minutes from now, an hour from now, a day from now, years from now, to be able to plan that effectively. And planning, that when we look at things like the need for new transmission network, how do we do the studies incorporating all of these new technologies and the new ways that they behave. So it's definitely things that we're dealing with in that space. Variability and uncertainty also brings challenges for what is called frequency control. Now, frequency control is all about maintaining the frequency at exactly 50 hertz on our grid all the time. We run a 50 hertz grid, and that is maintained by keeping load and generation on the grid precisely balanced at all times to keep the frequency at 50 hertz. If there's an imbalance of any kind between load and generation, then the frequency will start to shift. Now, we manage this to keep that frequency rock steady. We manage that with a variety of services, one of which is called regulation. This is the service for managing minor imbalances. So demand varies up and down all the time, from people turning on appliances and turning things off and so on. And those minor demand shifts have to be balanced by, for example, another generator that's shifting along with it to make sure that it's exactly matched all of the time. And that service that the generator is delivering by doing that is called regulation. Now, with more wind and photovoltaics coming into the system, we're looking at a lot more variability coming into our system. So it's not just minor variations in demand anymore. Now we're adding on the variability from wind and adding on the variability from photovoltaics, creating much bigger fluctuations that we need to manage. So we need more regulation services. And this is one of the challenges that we've been investigating, looking at how much more and when we're going to need it and so on. This, we've found, is particularly associated with large-scale PV plant. When you see fields covered with panel after panel, those large photovoltaic plant are particularly challenging because of their variability. So this is showing you a single day in the life of a large PV plant, and the output that it was generating over that day. And you can see these enormous spikes happening. And some of these are very fast. It might, in 5 minutes, drop from full output down to something very close to almost zero output, and then straight back up again. And that's just because this PV plant was dealing with a very cloudy day with intermittent cloud cover coming over the top. So its generation is quite spiky. So we're going to look at a grid that's got an awful lot more of this kind of generation in it, and we're going to need a lot more regulation service to manage that. So what do we do about it? What are the solutions that we're looking at? Well, there's a whole suite of things that we can do. Firstly, we can get a lot smarter about how we schedule regulation services. At the moment, we enable a pretty flat quantity of regulation all the time, but it's clear if it's driven by large PV, we need a lot more during the day and a lot less overnight. So we can get a lot more intelligent about how we schedule that service, and even to the point of including our forecast, where we can forecast those intermittently cloudy days and look at when we need regulation just for those. We can also create incentives for participants to manage their own variability, such that if you're operating a big PV plant, you might like to install batteries or something to smooth that generation, and we can create frameworks that make it worth your while to do that. Through payments to do it, or it could be through other sorts of frameworks. We can also bring in new sources of regulation. If we need a lot more of this service in future, We can get it from things like wind and photovoltaic plant themselves. So this example here is showing you a wind plant where we've given it a command to drop its output below its rated capacity. So it might be available, there's plenty of wind, it could keep generating at this level if it wanted to, but we've given it a command to drop down, which it does in the blue, and then we ask it to track along that pink line, and you can see that that wind plant is tracking pretty closely where it needs to be. So wind and photovoltaics are extremely flexible and extremely capable of following a set point as long as it's below their available power at that time. And that means they can offer us frequency control services. This is something that to date has not been done very much anywhere in the world, but we're running trials on this at the moment with a wind farm in our grid to be delivering this service and potentially providing that a lot of the time. So we've talked about frequency control in the context of the variability and uncertainty of renewables. It's also relevant when we think about the non-synchronous nature of wind and PV. So what does that mean? When we think about the generators in our power system, there's two broad kinds. There's synchronous generators and non-synchronous generators. The synchronous units includes the coal, gas, hydro, biomass, and some renewables as well, geothermal, solar thermal, and nuclear, because all of these generators are connected to the grid like this. They've got a rotor that's spinning with a magnet inside it, basically north and south, and as it spins, that magnet moves past these windings and creates a current in those windings, which then creates the 50 hertz AC signal that's what we have on our grid, our 50 hertz. So every single synchronous generator on the grid is spinning at 3,000 revolutions per minute, exactly in sync with each other. And I've actually found this out when I was a kid. My dad is an electrical engineer. He's down the front. Hi, Dad. My dad told me this when I was a kid, and it just blew my mind that we have hundreds of giant generators all around our grid, connected thousands of kilometers apart, and they're all exactly in sync with each other, spinning at 3,000 revolutions per minute, precisely. This is a very useful characteristic, because what it means is that if something gets out of balance, so for example, if a big generator suddenly trips off of the system, all of these generators have a lot of inertia. They're very physically heavy and spinning all at exactly the same frequency. So if something trips off and the frequency starts to shift, it will shift very slowly because that inertia is slowing everything down. So this is helpful to keep frequency stable because they're all spinning at exactly the same frequency. The non-synchronous generators, however, are fundamentally different in how they connect. So here's our wind and our PV, also batteries and flywheels, and they all connect to the grid through an inverter. So they're not through a turbine like this. A wind turbine, even though it is spinning, they've found that it's actually more efficient to allow it to spin at whatever speed it wants to have the aerodynamic efficiencies from that, and then connect it through an inverter so that it's decoupled from the system, and it can be a lot more efficient that way. Photovoltaics, of course, are completely different because there's no spinning parts. They use a completely different process to create energy, and batteries and flywheels as well, no spinning parts. So these non-synchronous technologies are fundamentally different. Now, inertia, this heavy weight of all of these spinning units, operates something like a brake on this scale. So it's slowing down those frequency changes, keeping everything stable. What this means is as the wind and PV displace our synchronous plant, the inertia on the system goes down and the frequency will start to change more quickly. It becomes more twitchy on the system. So when we look at an event, this is a typical event. If we're sitting at 50 hertz, everything's fine, and then all of a sudden a generator trips off that we weren't expecting, the frequency will start to drop, and that initial slope there is termed the rate of change of frequency, or the rock-off. And this didn't used to be a very important term, but it has recently become a very important term in our power system because it's something that we're now concerned about in terms of how we run our power system. Now, if that rate of change of frequency is too steep, if the frequency is changing too fast, This can cause all sorts of problems. For example, a generator, you can see a synchronous generator, if it's spinning at exactly grid frequency in sync, if that frequency suddenly changes very quickly, you can actually tear away the electrical coupling, the magnetic coupling inside the generator. And that's a very damaging event for that generator. So they will have protection systems that will trip the unit off to protect it from that event. And if we have too many units all tripping off, that can then turn into a cascading failure and black out the system. If it's really severe, the emergency control schemes won't work. So we have all sorts of control schemes that if we get the frequency gets too far out of bounds, can catch the system, and they won't work properly if we get to very high rate of change of frequency. So it's extremely important that we keep the system in a range of rock-off that we can manage. Now, this isn't just a problem for us. This is something that Ireland has been managing. Now, we keep hearing about Denmark and Germany and all these places doing innovative things with renewable energy, but actually it's the Irish that are really leading the way on these things because they have a small grid. They're a small island system with no AC interconnectors to anywhere else. So they're now at 24% renewable energy from wind, and they're aiming for 40% renewable energy by 2020. And they did a big study, a series of studies actually, that was to identify what the challenges would be as they moved further towards that amount of renewable energy. And they found from that that rock-off would be a major challenge for their grid. So they've had a work program in place for quite some years now to address this for our system. And I was very lucky to be able to visit them in January and have a chat to their system operators about the work program that they're doing and where the parallels are for us. And they're actually quite excited that they're not the only ones dealing with this challenge anymore. The fun part was walking around the streets and talking to everyday people in Dublin. And they'd ask, why are you here? I'm learning about renewable energy because Ireland is a world leader in renewable energy, and I'm here to learn about that. And without fail, they laughed, actually, because they thought that was hilarious that Ireland was leading the world. Very self-deprecating people. So for us in Australia, this is mostly relevant in South Australia. So we have, in South Australia, 42% of our energy is now coming from wind and photovoltaics. And that's all fine as long as the interconnector is in place, connecting it to the rest of the grid so it's all still one big grid. But if that one interconnector fails for some reason, which is very unlikely, it's a double circuit interconnector and you have some level of redundancy there, but it can fail on occasion, and that then leaves South Australia as a single island grid on its own with a very high amount of renewable energy and potentially a very low level of inertia. So what are the solutions? What do we do to address the problem? There's a whole range of things that can be done. So firstly, you can add more inertia. If you've taken away inertia with synchronous plant coming off of the system, add it back on. So that can look like keeping our synchronous generators running. And this is one of the things that we're doing as a short-term measure in South Australia at the moment to keep a certain amount of synchronous capacity running at all times to keep that system stable. But in the long term, that's probably not ideal. That means keeping gas turbines running a lot of the time, and gas is very expensive, and that translates through to high energy bills for South Australians. In the longer term, you could install new synchronous generators. You could install solar thermal or geothermal or biogas turbines to keep more synchronous capacity in South Australia. Or you can use synchronous condensers, which are a grid element that doesn't generate energy, but generates inertia, essentially, and sits and gives weight to the grid. And I'll talk more about those in a minute. You can also reduce the contingency size. So this is all about if the interconnector is flowing into South Australia at a very high level, and then we lose that interconnector, that creates an enormous imbalance event for South Australia, and you'll see a huge response to that. Whereas if you ramp the interconnector flows down to a very small level, and then you lose the interconnector, that causes only a very small disturbance in South Australia, which it is more likely to ride through. So this is another approach that we're using right now to reduce the flows on the interconnector to within bounds that are manageable. In the longer term, we're looking at a special protection scheme which would allow us to increase the flows on the interconnector, but to rebalance things in South Australia very, very quickly within milliseconds of that event occurring so that it can ride through those events more easily. You can also look at things like a new interconnector. if you've got 2 interconnectors into South Australia and one of them fails, you've still got another one as backup with more redundancy. And we're looking at that in planning studies at the moment. And you can also use things like fast frequency response, which is kind of my baby at the moment. So fast frequency response is all about giving a very fast power injection in something less than a second to correct the imbalance that's happened. So if a generator has tripped off, in less than a second we detect that that's happened and then give a very fast injection to correct it back into the power system. And this is something that wind turbines, photovoltaics, batteries, and demand-side customers can do to deliver this service very quickly, more quickly than synchronous generators on average. So to give you an example, this is what it looks like from a wind power plant. This is what's typically called synthetic inertia, if you've heard that term. We don't tend to call it that because it's not really inertia. It's a completely different service to give a very fast power injection. But with the wind plant, this is an actual event that happened in Hydro-Quebec system in Canada. So here's the frequency at 60 hertz. They run on a different frequency to us. And when the event happens, the frequency starts to drop. And here's what the wind power plant does. It detects that's happening and then ramps up its output and sustains that for about 10 seconds or so. And then it drops back off. So what's going on here is that the wind plant is using a very clever technology where it can extract the kinetic energy from the turbine blades and the drivetrain. So there's a lot of actual energy stored in the rotational energy of those blades, and it can extract that and put it back into the system as a pulse of energy. But it only lasts very briefly because those turbine blades will start to slow down, and then you need to re-accelerate the blades back up to their most efficient speed. So it will go into this recovery period where it's actually generating less than it was before. And this is something that we'll need to coordinate very carefully to make sure that we've got other services to match in and deliver everything stably and make sure that this doesn't actually cause a secondary event back into failure. So all of this process to get all of this working together, all these different services, needs to happen very quickly. This is within a few seconds of an event happening and then 10, 20 seconds out to coordinate all of this. So this is definitely not something where some person can be sitting at the control desk and hitting buttons to make this happen. This has to be very carefully programmed in an autonomous response that's pre-planned beforehand. So we've talked about frequency control in the realm of plant being non-synchronous. Plant being non-synchronous also leads to challenges around what's called system strength. So system strength is a measure of power system stability with regards to voltage, broadly speaking. So we talked about stability in frequency before, now talking about voltage. And it's related to what's called the fault current. So a fault is whenever something touches something in the power system that it really shouldn't be. So it could be conductors that are hitting each other for some reason. It could be a bushfire that's causing arcing or something like that. So when a fault happens in the power system, the synchronous generators in the power system detect that fault and push a huge amount of current into the fault. And that's really important that they do that because it helps us with all sorts of things. It triggers protection systems to detect that fault and isolate it so that it can clear very quickly. It also allows our wind and PV plant to ride through the fault and stay stable. And it helps to maintain voltage stability through that disturbance. So very important that we have enough fault current for all of these things to work. But the fault current comes from the synchronous generators. It's the coal, the gas, the hydro, and so on that are contributing that fault current, whereas the non-synchronous generators don't give us significant fault current. And even more than that, they actually require a share of that fault current for each wind and PV plant to operate successfully. So we can think about this with a simple analogy. So let's imagine we've got a boat, and the size of the boat is the amount of synchronous capacity that's online, the number of coal and gas generators that are operating on the system at the time. And the passengers in the boat are the wind and photovoltaic generators. So if we have a large boat, lots of synchronous generators online, and very few wind and PV generators connected, that's an inherently stable system. And if you have fault conditions, it will remain stable through those fault conditions. But we can get into weak systems in a number of ways. So a local weak grid is something like a wind farm, for example, that's connected at a very remote location, very far away from synchronous generators. So there's not a lot of fault current in that location. So that when a fault happens, that can cause a failure. So this is, for example, like the northern part of Tasmania. There's this wind farm, Muscle Row wind farm, in the far north part of Tasmania, which is a very remote location. Excellent wind speeds, which is why they decided to build it there. But a very remote location, and they had to do all sorts of really innovative things to install that in such a weak grid location and make sure that it operated successfully. A really world-class project in terms of demonstrating those sorts of capabilities. In system-wide weak grids, we might have a lot of synchronous capacity connected, but if we pile on a lot of wind and PV generators into that system, when a fault happens, they can interact with each other in really unfortunate ways that aren't helpful and can actually destabilize the system, leading through to a collapse. So the number of wind and PV plant also matters in terms of the total system strength. So when we project forward the amount of system strength that we're looking at, this map is showing you our calculations for grid locations where you might want to connect a new plant. And a green means that it's very high system strength. A red means low system strength. So you can see in these remote locations, we've already got places with low system strength. And we manage that with grid elements and the way we connect a new plant. In future, the trend is definitely towards system strength reducing in many more locations. So it's something that we're going to need to manage more proactively in future. Now, the main way that we can manage it, or the most straightforward way, is to add back in that fault current. And this is where our synchronous condensers come in. I mentioned them earlier because they can deliver us inertia and also system strength. So synchronous condensers are actually a really old technology. It's what we used to use in the grid back in the day, mostly for voltage management. And when you talk to older engineers, they really hate the idea of bringing these back because it's old technology. Now we use much better things with power electronics to give very sophisticated control of voltage. But what synchronous condensers can do that power electronics can't is deliver that inertia and the system strength. Because these things are basically like a generator. It's a big spinning turbine, essentially, or a big spinning generator connected to the grid in very much the same way, but just not producing energy in the same way. So it just keeps it stable and offers those system services. So they're kind of like a get-out-of-jail-free card. We can use these synchronous condensers to manage all sorts of problems. So we're looking at a future grid where our system services come from quite different places. So at the moment, the synchronous generators do pretty much everything for us. They give us our system strength, our inertia, our frequency control services. It's all fairly simple, coming from the same generators. In future, we're going to have a much wider range of participants providing all of these different services. So the system strength and inertia will still need to come from synchronous units, but it could be generators and perhaps synchronous condensers as well. Our frequency control will then come from a whole range of sources, the wind and PV delivering it themselves, storage units like batteries delivering frequency control services, and perhaps demand-side customers, industrial customers delivering balancing services, and perhaps even aggregated households. And we're looking at new services like this fast frequency response, or the synthetic inertia I mentioned, delivering services such that we can operate with less inertia successfully, coming from the wind and PV and batteries and so on. So it's a much more sophisticated system. It's a system where we're going to have to manage very carefully how all of these different pieces fit together in a much more sophisticated way. The next element is around the distributed nature of renewable energy, particularly rooftop photovoltaics is the big one right now that we're interested in, with all sorts of implications. If we're looking at a system with a lot of photovoltaics, that's very decentralized. So how will we operate that system without all the levers and controls that we have today from our big centralized power plants? How do we manage visibility in that system to know what's there installed on people's roofs and what it's going to do in any particular time? And then how do we model that? Particularly with things like disturbances, we do a lot of modeling to understand for different types of disturbances how it will ride through And we need to know what's there and how it's going to behave. So if it's on people's rooftops, it makes it much harder to have that information. So we have a program of work looking at all of these aspects. Of particular interest, it's worth mentioning South Australia again. South Australia has very high projections of continued growth in rooftop photovoltaics in particular. This chart is showing you the operational demand in South Australia, which means the demand that's left over after the rooftop photovoltaics have done their thing. So the blue line is what it looks like at the moment, and you can see already in the middle of the day there's a bit of a dip because of the photovoltaics eating away at the demand in the middle of the day. The dotted lines are showing you our projections for where we think South Australia might be going. And you can see in the middle of the day, the demand is getting lower and lower until by about 2030, it actually goes below zero. What that means is that all of the demand in South Australia is being met by photovoltaic systems on people's roofs. All of it. So there's big questions here about how we would deliver inertia and system strength, frequency control, how do we keep the system within network limits and make sure that we've got sufficient ramping capability to keep everything stable in that kind of a system. So big open questions at the moment that we're exploring. So to summarize, I've given you a bunch of information. All of the different challenges fall into kind of 4 broad categories that I talked about. We're looking at more variability coming into our system with more wind and PV, which means we'll need more regulation frequency control. And we can deal with this with more intelligent regulation systems and bring on new providers like wind and PV to deliver those regulation services and actively help us manage that variability. We talked about lower inertia from less synchronous plant online, leading to higher rate of change of frequency. And we can deal with that with things like fast frequency response, having much quicker responses in our grid, and also things like synchronous condensers to slow things down enough that we can deal with it. We talked about low system strength, bringing challenges in things like voltage control and protection systems, and we can deal with that with things like synchronous condensers as well. And finally, the potential for 100% of our energy to be coming from rooftop photovoltaics, with all of the controllability challenges that could come with that. And the solutions here will probably look like a suite of interventions, things like synchronous condensers for inertia and system strength, and potentially looking at things like aggregated services coming from those distributed resources themselves. The photovoltaic panels on people's roofs actually participating in these markets and helping to deliver the services that we need to keep it stable. So I wanted to finish just by noting that this is an ongoing journey. So we've come a long way from thinking about the sun won't always shine and the wind won't always blow. And we're somewhere in the middle here where we've identified the next suite of challenges that we're dealing with and working through as our system evolves. But this is going to be an ongoing journey. It's a transformation that will take an extended period of time. And as we go, new challenges will arise and we can deal with them as they come. So where are we going? We don't know yet, but we'll figure out when we get there. So thank you very much. I'm very happy to answer your questions. I think Joel's going to handle that. Thank you.
Fantastic, Jenny. All right, so we're now going to take some questions. So if you have any questions, write them down. You'll do a question slip on the way in, and Leonie or Dom will come around to collect those. Just wave them in the air for them. We'll give Jenny a chance to have a drink of water. A couple of little bits of housekeeping. Obviously, you've already been looking at Twitter and tweeting throughout the day, so you should totally follow BrisScience on Twitter, and you get kept up to date with all of the upcoming talks and events. You can also sign up to our website, Facebook page, and so forth. Next month we'll be back, July 17th, and we have Dr. Susan Hayes from the University of Wollongong. She's up for a conference, and she works on forensic facial reconstruction, which is where you take bodies and you try to reconstruct what their face would have looked like. And she's going to talk about some work she did, particularly with a case in New South Wales, and then the victim was eventually identified, and talk about how well those techniques work. But she does other work on the hobbits, the ancient species, small human, or who knows what exactly. So it should be a fantastic evening. Come along to that. questions coming around. I'll just grab a couple now. So one question from online already, if I can just find it again. So start with the tricky one. Are renewables more expensive than coal or gas?
Well, the cheapest thing is to keep running the system you have and just wear it into the ground. But that's really not an option from where we stand now. And in fact, these days, with gas prices going up and up and up, that's actually a really expensive option in some places. So for somewhere like South Australia, where gas is really the only option, there isn't a lot of coal-fired plant left, then renewable energy can be a really effective way to bring down the cost of that energy. We're probably right at the tipping point right now where wind and PV are becoming cheaper and cheaper, and coal and gas are becoming less and less cheap. And we're right at that tipping point where they are actually starting to stand on their own 2 feet as serious technologies. I think from our perspective, though, really it's about recognising that this transformation is happening, whether we want it to or not, and we have an opportunity to create the power system of the future and to genuinely lead in this space. So it's an incredibly exciting place for us to be, to create that system and make it one that we're proud of.
Fantastic. So we have a couple of questions which is around rooftop PV. And paraphrasing Adrian and someone else here, what if households and businesses with rooftop PV take them off the grid? What happens when people drop off the high-cost grid?
Yeah, so this is the effect that's often called the death spiral, where if some people start to drop off the grid, then the cost of maintaining that grid stays exactly the same, and it gets piled onto the people that stay, who then more of them decide to drop off until eventually nobody's on the grid anymore, and we've paid for this very expensive grid asset that we're no longer using. So it's a really difficult problem, and a lot of the question is about how we should be pricing the use of these assets, these expensive network assets that are there, and then how we make sure that we make decisions about building out those assets in future as well. So definitely something that we're thinking about how that system might look like. From our perspective as a system operator, it's a lot about how we would actually operate a grid where people are disconnecting, particularly if they're temporarily disconnecting and then coming back again. That's a much more complex system. So we're doing a lot of thinking about how that might actually operate and whether we or some other organisation should be actively managing that process.
Okay. Question from, it doesn't say, do you see a role for nuclear power in Australia in the future?
So nuclear power is obviously emissions free, which makes it very appealing, and it's synchronous and firm. So it has a lot of benefits over things like renewable, the wind and photovoltaics, for example. On the flip side, however, it is very expensive, and the trajectory for nuclear power is that it's becoming more and more expensive over time. And those costs are really different depending on where you are. So if you're in China and you want to build a nuclear power plant, you could potentially build that for somewhere approximating a reasonable cost. But if you're in a Western world country, the costs are fairly phenomenal when you look at what it's cost to build nuclear power plants in recent times. So I think it's very unlikely, even just on a cost basis, that we would see nuclear power coming into Australia. We have to also acknowledge that we have access to possibly the best renewable resources in the world and the widest suite of them. So in terms of the competitiveness and the other options that we have available, I really don't see it as very likely. But of course, if somebody wanted to connect, AEMO would connect them and we would integrate them into our grid.
Great. Brian asks, do you have a forecast for when our grid will be emissions zero?
It's in our planning studies at the moment, look at various different policies that are on the table. So the planning scenarios that I showed you in what we're looking at incorporate things like the commitments that Australia has made at the United Nations and think about how the electricity sector might be a part of those trajectories. So we are looking at some fairly significant reductions in greenhouse emissions with the sorts of scenarios we're considering right now. AEMO did do a study directed by the government to look at a 100% renewable grid. That was a couple of years ago now. And I believe it's probably still online. looking at how that 100% renewable power system might look. And it was very similar to the results that I showed you in the talk today as to how that system might operate. So a really interesting study if you want to have a look at it.
All right. We'll wrap up the grilling in a moment, but there are several questions here which are around politics and the role of different levels of government in energy policy. So you may want to make some general comments on that, but particularly I'll go with this one, which is more positive. How can we inform... I'm just saying. How can we inform opinion leaders that the wind and solar can't provide baseload myth is busted?
Yeah, it's a great question. We engage, AEMO engages with government at multiple levels, with state governments, federal governments and so on. And it is a process of working together to find solutions that work for the politicians as well as technically for the power system. So we engage with them very closely, and I don't envy them the situation that politicians are in trying to navigate public opinion on these issues. All I can say is that we work hard to have the best possible solutions on the table so that those are an option and that they're as cheap and efficient and cost-effective as possible.
Well, I think that is a wonderful note to finish on. So, ladies and gentlemen, could you please join me in thanking Dr. Jenny Riesz from AEMO. And don't forget, next month we will be back at The Edge, which is our regular home, and they'll be fully renovated, chance for you to sign up for all their workshops. I've done my 3D printing and CNC router inductions recently, so I'm ready to go and create lots of awesome things, so check that out too. And I'd love to invite you all to head outside, round to the terrace, and we'll have some drinks and I'm sure more discussion with Jenny. Thank you very much. See you all next month even.